problem?
We would like to challenge number 5.
Number 5.
Reject.
Reject.
Number 9.
We accept.
So you write down the name of reporter, opponent, and reviewer on the board.
这不是属于我的世界，他们看起来都是
Okay, thumbs up. Presentation of reporters for 12 minutes.
Honorable juries and fellow competitors, I'm the reporter from Team Excelsior. Today I'm going to report problem number 9, magnetic assist. Here's the problem statement. Attach one or two magnets to a non-magnetic and non-conductive base such that they attract the magnet suspended from a string. Investigate how the motion of the moving magnet depends on relevant parameters. Today, I'll mainly focus on what special moments does the pendulum have and how do different kinds of energy transform. This is the outline of my presentation. I will first talk about the phenomenon, which includes the observation, the setup, and the qualitative explanation. Then I will talk about the theoretical model. We will talk about the coordinate and the Lagrangian equation, and the dissipative and the converge ratio. Then for the experiment, we will have discuss the effective distance and the multiple gears and the converge ratio. For the discussion, we will talk about the chaoticity and the energy transfer. Here's the phenomenon. This is the magnet that's the pendulum magnet, and this is the bottom plate magnet, and the force inside this diagram will have the force of mg, which is the gravitational and the gravitational mass of the pendulum, and also the T is the force that the string connects with the magnet, and also Fb, which means the force that the two magnets can contact with each other. And according to the law of conservation of angular momentum, if we ignore the dispersion, the vertical direction of the system will be the same. So it will stay at the same point, and we can calculate the law of conservation of angular momentum by this formula. And the magnetic force increases when the tiddling angle decreases. Here's the energy analysis. So there will be we separate this phenomenon into two conditions. When the pendulum has a higher degrees of theta, which means the degrees between the string and the vertical line, and the kinetic energy will mainly transform with the potential energy, which is provided by the gravitational force, which is mg. And the constant dispersion of this phenomenon will be an air drag and eddy current. So because the distance between the two pendulum will be very far, so the potential energy provided by the magnet won't affect the phenomenon. Won't affect the phenomenon obviously. And when there is a lower degrees of theta, the kinetic energy will then have an effect with the potential energy provided by the magnet. And though the transformation of the kinetic energy and the gravitational potential energy will still remains, but it will be less comparing to the potential energy with the magnet provided. And constant dispenser still is the air drag and the eddy current. And then is the theoretical model. We will use the Lagrange equation to investigate this phenomenon. And to measure the field of the dipole moment, we use a Gauss meter to measure the field, the magnetic field. And this is a graph that shows the obtained dipole moment mu by measuring. And we assume the magnetic field is uniform, so we can fit a line of the measuring. Then is the calculation of the magnetic potential energy. Since the system is radially symmetric, so only theta affects the phenomenon. So we don't need to consider other we don't need to consider other degrees. And the magnetic field will be this equation, and the magnetic potential energy will equals to the mu P dot B. And the parameters we use is in here. And this is a graph showing the thickness of the magnetic field. So this is the equation of motion. We use the kinetic energy and the potential energy to calculate this phenomenon, and also we use this formula to calculate the equation of motion, which considers the spinning angle phi and the swinging angle theta. So about damping, because there will be a damping in this simple pendulum, so we fitted a line on the according to the experimental data, and the damping equals the 0.058. We use the collaboratives to solve the Lagrange equation and spider to numerical the solution. This is the simulation of the experiment. This is when we give a force to the sideways of the magnet. It will create a 3D motion of 3D motion of phenomenon, and this is when the pendulum only swings at the 2D motion. And then it's the experiment. So this is the varying pendulum length, which in the 2D pendulum condition. So the time of the pendulum length swings, and the length is when the length of the pendulum string increases, the time that the pendulum swings increases. That's because a very simple reason is because it is the same phenomenon with a simple pendulum. And when we changes the angular velocity, it will have this graph that shows the connection between the angular velocity and the direction. So if we it will when the angular velocity increases, the direction will increases. And then it's the varying pendulum length of 3D motion. So that is another experiment of the previous experiment we did before, but this time it is in a condition of 3D motion. And when the length of the pendulum string increases, the duration will increase. and we solve the equation of motion using Python. So this is our simulation of the this is the discussion. For the chaoticity of energy. Okay. So we input all the parameters inside this Python, and we can animate the phenomenon just like we did in the previous observation video. The reason why we didn't use the damping with two, we actually put the damping here. The swing will swing like on the left and the right, and this is the left side and this is the right side. We actually flipped off this this side of the graph to have a average damping of to calculate the average damping of the experiment. And that is why one of the reasons that the pendulum was stopped, and also that there will be two reasons to cause the pendulum to be fully attracted by the magnet at the bottom. One is because of damping, and it is the same as the simple pendulum, and another is caused by the attraction between the magnets. Thank you.
Okay. Question mark, comment. 2 minutes.
So thank you for presentation. And the first question is, how do you calculate your error bar? How do you calculate your error bar?
We did the experiments many times, and we will.
Average, right?
Yes,
Okay,
average.
thank you. And the next question is, do you consider the magnet a single point or a object?
We consider the magnet as the
Single point.
middle of the pendulum, which is
So center of the mass.
yes, center of
Okay,
the mass.
And the third question is, do you have observation video? How can you ensure that your observation video is the same as your simulation?
Since we compared the like these are the actual experiment, that is not simulation.
Okay.
That chart
Is this
of
your data or your?
this is our data.
Okay. Thank you. And do you have simulation model?
Yes, which is the Python. We
No.
use
I mean some business model.
we use the equations that like the Lagrange equation of the motion to write inside the Python.
Okay, thank you.
Python.
And you mentioned that you consider the chaotic system. Did you do some
We
research?
found
on that?
out there is a chaotic system when there are multiple magnets under the.
So what situation did you consider about the chaotic system?
Oh, we just found out there will be a.
And did you consider another force?
Okay, thumbs up.
Thank you.
The version of opponent for 3 minutes.
第一个我问那个谁好了，因为他没有做完成，那个 problem statement 完全全部做你跟队长还是那就没他想想说法，他的那个
可以一个角度。
Time's up. Opponent paper of question 4 minutes.
So hello everyone, I'm opponent from variable 1. And today I would like to oppose number 9, magnetic assist. And the problem statement is attach 1 or 2 magnets. The problem statement says 1 or 2 magnets, so I just see one magnet in the presentation. And to a non-magnetic and non-conductive base such that they attract a magnetic substance from a string, investigates how the motion of the moving magnet depends on relevant parameters. So I think the main focus might be what kind of spatial motion and how the energy transfer. And here's the overview. The first one is I think that the lack of photo or video, like something like observation video, so I cannot see how could they conduct the experiment. And the theory, they use the conservation of the momentum, but they say while the time length angle increase, magnetic force increase, but I think there's another force, so this theory might be not correct. And they talk about the potential energy, like gravitational energy and kinetic energy, and like that equation. And this equation is a simulation. Is the simulation models they use. But I would like to ask her because she didn't show me this equation. And they consider only angle affect the phenomenon, but I don't think so. I think there are other parameters will affect that, and they consider the damping effect and the experiment. This one is measurement. They measurements the dipole moment. And the experiment, this is their independent variable. And they have a varying pendulum length and the angular velocity. And the simulation is, as I mentioned, they didn't have the models of simulation. And the conclusion, I think they lack of conclusion because they didn't talk about when some parameters increase and the resource will decrease or like something else. So here's the discussion points. The first one is I would like to ask with the position that you measure and unaffected result and the set of like observation video and the sensor of magnet because she said she considered the magnet as a point like they use the center of mass to as a point. And they have different numbers of magnets because they didn't do this experiment. And it's chaotic system because she mentioned that she considered the chaotic system, but I don't see any, I didn't see any like theory or something to explain about the chaotic system. And simulation models and results and single pendulum. I don't think single pendulum is okay for this theory because single pendulum has only one force to like the tension, but there is other force, so we cannot use single pendulum. So I would like to invite the reporter onto the stage.
Discussion.
So could you please show me your presentation? So the first question is, I want to ask how do you conduct the experiment? I want to know
Can you
how to
define what is conduct the experiment?
Yeah, do you have observation video?
Yes, we do actually.
Or some pictures about it? Okay. So
This is the picture of the actual.
You just put the magnets on the bottom of the.
This is the observation video for. This is observation for damping. Damping is the definition of damping is just caused by maybe like air resistance and friction. We are in this PowerPoint we are only we are only calculating the damping. So that's why there are only one pendulum here.
Is damping affect your own experience?
It affects the throughout the whole time of the experiment because since the pendulum is moving, it will have like forces like.
But I think you should calculate how the
amount of damping is actually here.
So could you please explain this again? Because you didn't show me in which conditions.
We fixed it the line. Sorry. So this is the equation that we use for explaining what is the damping of this pendulum. So it will be 0.05.
So have you calculated the damping coefficient?
Yes.
Damping coefficient is like this, but how can you calculate it? If you use data to calculate it, it's not correct.
It is always a constant number throughout the whole time of the experiment. So it is important for us to first know what is the damping.
So the damping system is your boundary condition of your is your initial condition, right? Is your
it will go throughout the whole experiment. So yes, it is an initial.
So it is constant, or it will change by the experiment.
It will be a constant.
So how can you show me why it is constant? Now, could you please show me the data that the damping system is all constant?
The cost of the damping will not be constant because the damping is to describe like how would energy lost in this system.
So what is the function of the entire of this one?
We compared this graph to the.
So did you fix the damping effect to your theoretical model?
Yes.
Could you please show me that? So could you please show me in your like formula or some theoretical model? Not this one. I mean, So next stage. So let's go to next stage. So what is other observation video in other stages? Did you recall that?
We can first talk about other questions and I will show you later.
Okay. And the next question is chaotic system.
Yes.
Because you talk about chaotic system, but you didn't show me about.
Because the definition of chaotic system is like when you change a little.
Yeah, I'm not
Like
asking.
yeah, but the experiment is extremely hard to do because it is very hard for us to have a like the
So what do you
start
guess
with the
chaotic system will affect? So can you what do you guess? The chaotic system will affect your experiment results. Do you have something?
it won't be completely like there won't be like there would be a pattern, but the pattern is like a big
So
we cannot predict the
So you cannot
place.
predict.
Yes.
If something you cannot predict is chaotic, right? Am I right?
Yes, but we can predict
No,
like
I
the
don't think so because
the-
chaotic has its own condition, right?
yeah, but we can we can predict the area of the
So
The
you
experiment.
didn't do this kind of experiment, right?
yes.
Okay, so next stage. Did you measure the string as the string length or the string plus magnet as the length? So that's right. Thank you. So it's this one. It's this. It's your length. Like this. It's your length. Or like the center of the length.
Yes, this one is the length of the center.
So this one is your length, right?
Yes.
So there's extra force on the pendulum, right?
Yes.
You regard it as a single pendulum.
We call it a single pendulum just because there are some similarities with the simple pendulum when
But-
we
But it has extra force, so I don't think it cannot be.
no we are just like separating the
Could you please show me the video of the not video, it's your slides about the single pendulum. In your because you talk about it.
we assume that when it is in a higher degrees of theta, it will be similar to a simple pendulum. And the reason why we separated the simple pendulum and the effect of magnet is just because we want to analyze the force like this separated.
Okay, so I don't think this one is not not like this one because the energy is potential energy like gravitational energy transferred to the kinetic energy. But there's other energy like magnetic energy, right? So it cannot be used to assume that it is a single pendulum, right?
We actually calculated the field that affects the pendulum. Like in this part of when the pendulum swings to this part of the system, it will be mainly affected by the magnet, and we did calculate it in
So
our
this one is a magnetic field, right?
yes.
So in your experiment, you say that you calculate you regard the magnet into the center of mass, right?
Yes.
And how can you calculate the magnetic field? Because magnetic fields might be not all the same in your experiment. So how can you calculate it? Because you have this.
We already. This is where we measure like we measure every distance of the like between the magnet and the force meter, and we can use those data to predict the whole.
So please show me how you do this one. In this.
This is the experiment of measuring the magnetic field.
So how can you measure the magnetic field? Like by what kind of sensor?
Force meter, a gauge meter.
Okay, thank you. And so next stage is the problem statement. Because the problem statement mentioned that you have to consider relevant parameter, right?
Yes.
So what do you think which one is relevant parameter?
Like the distance between the.
So do you have conclusion? Because I didn't see conclusion in your presentation. And did you list the relevant?
We think we already explained the phenomenon clear enough, and there's
but I didn't see any conclusion because you have to have conclusion. Do you have that? Oh, okay. Fine.
No.
So problem statement mentioned that one or two magnets. Yes, one or two because but did you do two magnets in the base?
as we
Could you please show me the data? If you did. Two magnets.
it's like
No,
as we mentioned before, it
Okay,
will have
I'm
a.
sorry. I want to summarize the discussion for 1 minute.
So I would like to summarize the discussion. The first one is setup. Only the photo of damping, not procedure. And they didn't have another video of that. And damping use data to calculate the damping coefficient. Now didn't show the data physical equation. And we think damping is important initial condition in chaotic system. Reporter should be proof the damping is constant. And the third one is chaotic. Reporters say if the system is not predicted, it's chaotic. But within the definition of chaotic is that it depends on initial conditions. And the reporters think that it's single pendulum, but according to analyzer 4, it's a single pendulum. But opponents think the magnets in the magnetic field, there's another force besides gravitational force. And different number of the magnet,
Okay, time's up. Question of review to reporter and opponent for 3 minutes.
So this question is for both of you. Do you think that damping is the main factor that makes the magnet stop?
It is one of the factors.
It's
not
the major
main.
one.
Not the main.
Major one.
I think it's a factor because reporter has discussed about that in.
Okay, thank you. So you mentioned a lot of damping force that acts as a factors in your experiment. So do you calculate the damping coefficient?
Yes, which
Yes.
is 0.058.
Okay. And this one is for opponent. So you mentioned there's a lack of evidence that shows the experiment has a damping force, and also the reporter has a lack of calculation of the damping coefficient. So what can you suggest to the reporter to improve his experiment?
I think the reporter should add the damping force to their theoretical model.
Oh, okay, thank you. So this question is for the reporter. So do you recognize that damping should only have so it should not have the E without the constant number before it? The calculation of damping force should only have E, the energy.
What's the question that you want to ask?
Okay, thank you. So the problem statement says that there's a string that you need to attach a magnet on the string. So do you use a string in your experiment or use a stick?
We use a string.
Use a string, okay. And
It's a fishing string.
so this one is also for the reporter. So do you acknowledge that there's a specific definition for the chaotic system?
Yes, it's when you change a little bit of your initial maybe force, and it will be a completely unpredictable.
Okay, thank you. So when we what specific time interval will you think the magnet exhibits the unpredictable motion? Push as you mentioned.
We didn't measure the time interval, but we can assume that we can predict that the chaotic chaotic system will.
So this question is for the opponent. So you mentioned that you questioned a reporter about the release position and how much force when the magnet is released. So what do you think can when considering this factor, how could this improve the experiment?
So, what's the question?
Like, how will the release position and release force of the magnets affect the whole experiment?
I think the release point will affect the magnetic field, and also affect the track of
Okay,
the.
time's up. Preparation of reviewer for 2 minutes. Time's up. Review explore for 4 minutes.
Good morning, honorable judges, fellow contestant, and esteemed guests. I'm a reviewer from TYPT Local, and today I'm going to review problem number 9, magnetic assist. So here's the problem statement. And here's the phenomenon. So the swinging magnets will be affected by the magnets attracted on the base, and the gravitational force or tension and the magnetic force will act as the main factor of this experiment. So here's the theory that the reporter used and the experiment. And yeah, the reporter thinks that the system is relatively symmetric and only zeta affects the outcome, and they neglect any other factors. So here's some pros and cons of the reporter. So I think she has a good and complete theory deviation, and she also has a thorough explanation of this phenomenon. However, there could be some improvement, such as I think there's a lack of experiment data, and also there's lack of clear demonstration of, and also the lack of definition of many terms. And here's pros and cons for an opponent. So I think they give a lot of their own opinion about how to improve the whole experiment, and also suggest that reporters should include more variables, which we also agree with. And for the cons, I think they should not focus on the numbers of the magnets, as it's not significant in reporter's presentation. Next. So the discussion 1. The opponent asks the reporter how do you conduct the experiment, and how do they observe the video, and how damping affects in this experiment. And reporter responds with the observation of damping is shown on the PowerPoint, and yes, there will be a constant effect throughout the experiment of the damping force. And our opinion about that is, if you use a damping model, it will not have the constant addition to the equation. And discussion 2, the opponent questions the reporter about how chaotic system will influence the whole experiment, and there's no experiment to prove or any evidence to prove that damping force exists in this experiment. However, the reporter responds with there will be a pattern of the magnets, and it cannot predict. So they think it can simplify as not simplify, but acts as a chaotic system. And our opinion is that since the definition of the chaotic system is unclear, they need a calculation to prove the damping coefficient. Discussion 3. So the opponent asks, how can you calculate a magnetic field? And the reporter responds with, they use data to make an empirical assumption. And our opinion is that they need to use 1D magnetic force equation to calculate the magnetic dipole moment. For discussion number 4, the opponent asks the reporter how the center of mass will affect the system, and the reporter said it will not affect the system. And we think it will cause torque and rotation throughout the experiment, and also the center of mass is on the next. And discussion number 5, opponent questioned the reporter about her conclusion and about adding 1 or 2 magnets on the base will affect the whole system, and also questioned about the any video evidence of their experiment. And the reporter responds with this. They will later on add like some videos or evidence to prove their experiment. Yeah. And I think there's several missing points, such as the connection between the magnets and the base, or 2D or the 3D definition, and the force diagram is not correct. Force direction and force direction.
Hands up. Concluding remark of the reporter for 2 minutes.
Honorable juries and fellow competitors, I'm the reporter, and I'm here to explain some concluding remarks. The first one is the damping acts throughout all of the experiments, as we mentioned, and it is the constant throughout the experiment. And we conducted the experiment and has compared it to the simulation model, which it mainly appears here. And one can explain the motion with or without the Lagrange equation, and the Python codes presented within the report is the simulation of the experiment, because we want to neglect other factors that maybe the manual experiment would exist. And also the reporter has measured the magnetic field, and we draw it into a graph, and which we mentioned that we assume that it will be the field will be uniform, and because we have the damping coefficient, because the friction between the string and the upper plate would be a constant, and the speed within the system won't be very high, that the air resistance will have a significant change. So the damping force, we assume it will be a constant. And throughout the whole discussion, we did draw a lot of the graph about the magnetic field, and we also fitted a line to make sure that it's a linear ball data. Thank you.
Okay, hands up. Question of jury. Any question?
Let me start from the report. You said the magnetic pendulum, its motion is 3-dimensional, right?
Yes. Yes.
Give us a simple explanation why it's 3-dimensional instead of 2-dimensional.
Because if you give the
No, just give.
the reasons. It will not be vertically on top of the magnet at the bottom. It might have
I mean, what's the reason for three dimension?
giving a force, like
Force, what kind of force is,
initial
why is?
force. Giving another direction of initial force, it will cause the
No, if it's a simple pendulum, it's in two dimensions, because it's only, the force only depends on what? And on the other hand, the magnetic force, why is it different?
in the simple pendulum, it it will be 2D because it only depends on the gravitational force and the exchanging between the potential energy and the kinetic energy, and it is because of the gravity. The 3D is
Okay. Maybe we can explain later, okay? Because three-dimensional must be a reason, right?
So
So let me, maybe Holden, let me ask you, you talk about the damping force. What's the origin of the damping force?
I have mistake here because damping is not a force, it's a effect on the system. So,
Now, what's the origin of the damping force? If we call it damping force.
oh no, it's not force.
Yeah, if
I-
we call this kind of force a damping force, of course, there's a damping force. If we call it, it's not real force, but if we call it damping force, what is the origin of the damping force?
It's something like environmental factors such as
What's,
friction.
for example, what is the mathematical form typically?
Mathematical form,
Yeah,
like because
depends on what?
depends on the material, like friction, because of friction may cause this one.
Let me, what's the magnetic pendulum is periodic motion. What's the frequency of the magnetic pendulum?
actually,
You guess, make a guess, what's the,
in my opinion, I don't think the magnetic assist experiment will act as a
no, it's a
stable
periodic
frequency.
motion, right? It's-
Yeah, but
So what's, make a guess, what's the frequency? It's just one swing. What's the time for the one swing, for example? One period,
Depends on
make a
the-
guess.
But okay, maybe 2 seconds.
You know simple harmonic oscillation, what's the periodicity, what's the frequency of the simple harmonic oscillation, do you know?
Yeah, but
Do you remember that?
yes, but in this experiment,
Yeah.
I don't think it. So I think there's many factors that affects.
Okay.
Yeah.
Yeah.
Okay, thank you. Any questions?
I just have a brief question about the opinion. So you keep mentioning that there are some missing parameters. So what is the major missing parameters in that is possible?
I think the parameter like the shape of the magnet, because the shape of magnet will affect the magnetic field.
So that's the key parameter you see.
I think that this one is one of the parameter of that.
So how about it?
So I believe the initial position will be the main factor that affects the outcome of this experiment.
So how about it?
I do not think like the shape of the magnet will affect have a significantly effect on the magnetic field, because we already assume that the magnet is in a one point.
Maybe I expand a little, okay, because maybe I asked too fast. So you can say maybe a few words in response to my question. Why is three-dimensional? The motion, why is it three-dimensional instead of two-dimensional? And the simple pendulum is two-dimensional. It must be related to force. So magnetic force has some characteristic. What is it?
It's
Depends on what angle.
Depends on the initial force, like
The theta
angle
or
of-
phi or both or.
No, the angle of phi
And
and the
so it makes it three-dimensional. Yeah. So you want to add a few, because you talk about the damping force a lot. So just make it clear. What is the origin of the damping force? Yes, it's not a real force. Okay.
Yes.
It's a dragging force. But it has a typical mathematical form. It's related to what?
It's related to the air resistance and velocity.
Velocity.
Yes,
Okay.
velocity.
Okay. It typically related velocity of the motion. I forgot what I asked you.
About the frequency of, yeah.
Pendulum, any pendulum, the key characteristic is its frequency. So it's period of time. So when you see that, you can immediately make a guess what's the frequency of that motion. So you can start from the simple harmonic motion. It's k over n square root. It must be similar to that, right? So you can make a guess. What's like a k in this case, what is like n in this case, and you can make a guess. Of course, it's a three-dimensional, it's a little bit complicated. Yeah.
Thank you. Please, take the floor. Please show the score of reporter. 4, 5, 5, 6, and 6. Okay. Please show the score of opponent. 6, 8, 5, 5, and 6. And please show the score of reviewer. 6, 7, 6, 5, and 5. Okay, any comments on this side?
Let me maybe very quickly, for the mechanics, the simple harmonic motions, the most important part. But it's very typical. All the pendulum follows the same characteristics. So we better start from the simple harmonic motion, the simple pendulum, and magnetic pendulum. That's my opinion.
Any comment? 好，那我们这个饭就到这边好，那我们休息10分钟。好，对，10分钟，因为有点累了。好，那